Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, and their impressive abilities in understanding and generating natural language. However, we recognize that LLMs face difficulties with complex reasoning and accessing current information from external sources. To overcome these challenges, we need to enhance their reasoning skills and improve their interaction with search engines. We categorize existing methods for integrating LLMs with search engines into two main types: retrieval augmented generation, RAG, and using the search engine as a tool. RAG retrieves relevant information based on a query and incorporates it into the LLM's context for generating responses. While this method allows LLMs to use external knowledge, it suffers from inaccuracies in retrieval and lacks the flexibility needed for multi-turn interactions, which are crucial for complex reasoning. Alternatively, we can prompt or train LLMs to use tools like search engines during their reasoning process. However, prompting methods often struggle with generalization, as they may not cover all tasks encountered during pre-training. Training methods offer more adaptability but require extensive, high-quality annotated data, making them hard to scale. We note that reinforcement learning, RL, has emerged as a powerful approach to enhance LLM reasoning. Models like OpenAI O1 and DeepSeek-R1 have successfully used RL techniques to improve logical reasoning and problem-solving by learning from experience. After RL training, models can develop complex reasoning skills, including self-verification and self-correction. However, applying RL to search and reasoning scenarios presents three main challenges: integrating the search engine into the LLM's RL framework while ensuring stability, enabling iterative reasoning and search calls, and designing effective reward functions for these tasks. To tackle these challenges, we introduce Search-R1, a new RL framework that allows LLMs to interact with search engines in a more integrated way. Our key innovations include modeling the search engine as part of the environment, supporting multi-turn retrieval and reasoning with specific tokens for search and information, and using a simple outcome-based reward function that proves effective in search and reasoning tasks. In summary, our contributions are threefold. We identify the challenges of applying RL to LLM reasoning with search engines, propose the Search-R1 framework with features for stable optimization and complex task solving, and conduct experiments showing significant improvements over existing methods. We also provide insights into RL applications for reasoning and search, including method selection and response length considerations. Section Summary. In this section, we discuss the limitations of large language models, LLMs, in complex reasoning and their integration with search engines, highlighting two main approaches: retrieval augmented generation, RAG, and treating search engines as tools. We introduce Search-R1, a novel reinforcement learning framework that addresses key challenges in this integration by enabling interleaved reasoning in search, supporting multi-turn interactions, and utilizing a simple outcome-based reward function, demonstrating significant improvements over existing methods. Section: Large language models and reinforcement learning. In this section, we discuss large language models, LLMs, and reinforcement learning, RL. RL is a method where an agent learns to make decisions over time by interacting with an environment and receiving rewards, with the goal of maximizing total rewards. We introduced RL to LLM tuning through reinforcement learning from human feedback, RLHF. This method first creates a reward model based on human preferences, which then helps tune the LLM using RL techniques, often through the proximal policy optimization, PPO, algorithm. However, PPO requires several optimization rounds, making it complex to implement. To simplify this process, we have proposed direct optimization methods like direct preference optimization, DPO, and SIMPO. While these methods are more efficient, they face off-policy challenges and may not always perform as well as traditional RL methods. Other alternatives include Group Relative Policy Optimization, GRPO, which estimates baselines from group scores without needing a critic model, and RLOO, which offers a simpler optimization framework. Despite these developments, Using RL for LLM-driven search engine interactions and reasoning is still largely uncharted territory. Next, we present the detailed design of Search-R1, which includes 1. RL with a search engine, 2. Text generation with interleaved multi-turn search engine calls, 3. The training template, and 4. Reward model design. For RL with a search engine, we define our framework to maximize the expected rewards based on the policy LLM and the reference LLM, while incorporating retrieval and reasoning. This means we explicitly include search engine results in our decision-making process, which helps in tasks that require external information. We build on established RL methods like PPO and GRPO to enhance our approach. In terms of loss masking for retrieved tokens, we compute the token-level loss over the entire rollout sequence, which includes both LLM-generated and retrieved tokens. While optimizing LLM-generated tokens helps the model interact better with the search engine, applying the same optimization to retrieved tokens can create issues. To solve this, we implement loss masking for retrieved tokens, ensuring that we only compute the policy gradient for LLM-generated tokens. This stabilizes training while allowing for flexible search-augmented generation. When using PPO with a search engine, we aim to optimize LLMs by maximizing a specific objective that involves both the current and reference policy models. We draw input samples from our dataset and generate outputs that include results from the search engine. We also apply a token loss masking operation to differentiate between LLM-generated and retrieved tokens, which helps stabilize training. For GRPO with a search engine, we enhance policy optimization stability by using the average reward of multiple sampled outputs as a baseline, rather than relying on a learned value function. For each input question, we sample a group of responses from the reference policy and optimize the policy model based on these outputs. We also apply token loss masking and directly incorporate KL divergence into the loss function, ensuring that we account for retrieved tokens when calculating this divergence. Section Summary. In this section, we explore the integration of reinforcement learning, RL, with large language models, LLMs, through methods like proximal policy optimization, PPO, and group relative policy optimization, GRPO, focusing on optimizing LLMs for reasoning tasks that involve external information retrieval. We also introduce loss masking for retrieved tokens to stabilize training and enhance the model's interaction with search engines, while outlining our framework for effective decision-making in reasoning-intensive applications. Section: Text generation with interleaved multi-turn search engine call. In this section, we describe our process for generating responses using a large language model, LLM, that incorporates interleaved multi-turn search engine calls. We approach this in an iterative manner, where the LLM alternates between generating text and querying an external search engine. When the LLM needs to perform a search, it is instructed to place its query between two specific tokens, which we denote as search call tokens. Once these tokens are identified in the generated text, we extract the search query, query the search engine, and retrieve relevant information. This information is then enclosed within special tokens and added to the ongoing sequence, providing additional context for the next generation step. This iterative process continues until we either run out of search engine call budget or the model produces a final response, which is marked by designated answer tokens. To train our model, Search-R1, we create a straightforward template that guides the LLM to follow our instructions. This template organizes the model's output into three parts: reasoning, a search engine call, and the final answer. We intentionally keep our constraints to this structure to avoid biases and ensure that the model's learning remains unbiased during the reinforcement learning process. For reward modeling, we use a rule-based reward system that focuses on the correctness of the model's responses. We evaluate correctness based on exact matches between the model's answer and the ground truth. We do not include format rewards since our model already adheres well to the required structure, and we plan to explore more complex rewards in future work. Additionally, We avoid using neural reward models due to their vulnerability to reward hacking and the added complexity they introduce. We evaluate Search-R1 on 7 benchmark datasets, which we categorize into general question answering and multi-hop question answering. These datasets present a variety of challenges, allowing us to assess Search-R1's performance in both single-turn and multi-hop retrieval scenarios. To measure the effectiveness of Search-R1, we compare it against several baseline methods, including inference without retrieval, inference with retrieval, and fine-tuning-based methods. We ensure a fair comparison by using the same retriever, knowledge corpus, training data, and LLMs across all methods. In our experimental setup, we utilize 3 types of models and use the 2018 Wikipedia dump as our knowledge source. We standardize the number of retrieved passages to 3 for all retrieval-based methods. For training, we combine the training sets of 2 datasets to create a unified dataset for Search-R1 and other fine-tuning methods. We evaluate performance using exact match as the metric and conduct experiments on both base and instruct models. For training Search-R1, we set specific learning rates and parameters for our reinforcement learning methods, with PPO as the default method. Section Summary. In this section, we describe our iterative approach for generating responses using a large language model, LLM, that alternates between text generation and search engine queries, guided by specific tokens to manage the process. We also outline our training methodology, reward modeling, dataset evaluation, baseline comparisons, and experimental setup to assess the performance of our model, Search-R1, across various question-answering tasks. Section: Performance. In this section, we present the main results comparing Search-R1 with baseline methods across 7 datasets. Our findings, summarized in a table, show that Search-R1 consistently outperforms strong baseline methods. We achieve average improvements of 26%, 21%, and 10% with the models Qwen 2.5-7b, Qwen 2.5-3b, and Llama 3.2-3b, respectively. These improvements are evident in both in-distribution evaluations, like NQ and Hotpot QA, and out-of-distribution evaluations, such as Trivia QA and others. Search-R1 also surpasses reinforcement learning-based training for reasoning without retrieval, which aligns with our expectations since integrating search enhances access to relevant knowledge, boosting performance. We find that Search-R1 works well for both base and instruction-tuned models, demonstrating that our approach can effectively apply reinforcement learning with outcome-based rewards to reasoning with search, extending its previous success in pure reasoning contexts. Moreover, Search-R1 generalizes well across different base models, including Qwen 2.5 and Llama 3.2, unlike some reinforcement learning methods for mathematical reasoning that only work with specific models. Our results suggest that search-augmented reinforcement learning is more widely applicable across various model families. We also compare different reinforcement learning methods, specifically PPO and GRPO, using Llama 3.2-3b and Qwen 2.5-3b models. Our training dynamics comparison reveals that GRPO converges faster than PPO because PPO needs several warm-up steps due to its reliance on a critic model. However, PPO shows greater stability, as GRPO can lead to reward collapse in certain models, while PPO remains stable across different architectures. Despite these differences, both methods achieve similar final reward values, indicating they are both effective for optimizing Search-R1. Our evaluation results show that GRPO generally outperforms PPO, achieving higher average performance across both models. The instruction-tuned variants perform better than the base variants, with Search-R1 Instruct, GRPO, for Qwen 2.5-3b achieving the highest average score, while Search-R1 Base, GRPO, for Llama 3.2-3b follows closely behind. We analyze the training dynamics of Search-R1 across base and instruction-tuned models, observing that instruction-tuned models converge faster and start with higher initial performance. However, both types achieve similar final performance after training, suggesting that reinforcement learning can effectively help base models catch up over time. Lastly, we conduct an experiment with Search-R1 using the Llama 3.2-3B base model, focusing on training reward and response length dynamics. Our results indicate that in the early stage, response length decreases sharply while training reward slightly increases as the model learns to eliminate filler words. In the mid-stage, both response length and training reward increase significantly as the model learns to utilize the search engine. Finally, in the late stage, response length stabilizes around 500 tokens, indicating convergence, while training reward continues to rise slightly. Section Summary. In this section, we present that Search-R1 consistently outperforms baseline methods across various datasets, achieving significant improvements in performance, particularly with instruction-tuned models. We also find that GRPO converges faster than PPO while both methods yield comparable final rewards, and our analysis shows that instruction-tuned models initially perform better but both model types achieve similar final outcomes after training. Section: Study of Retrieved Tokens Loss Masking. In this section, we study token-level loss masking for retrieved tokens to avoid unintended optimization issues. We evaluate its effectiveness by looking at how it affects training stability and model performance. We conduct experiments using the Llama 3.2-3B base model, comparing training dynamics with and without the loss masking. Our findings, illustrated in Figure B, show that using retrieved token masking leads to better improvements in the language model, reducing unintended optimization effects and ensuring more stable training. The performance comparison in table indicates that Search-R1, which uses retrieved token loss masking, consistently outperforms the version without it. For deeper insights into Search-R1, we perform a case study with Qwen 2.5-7B base, comparing its behavior with reinforcement learning that does not use a search engine. The results in table reveal important observations. First, we find that interleaved reasoning and retrieval enhance problem analysis. Search-R1 allows the language model to engage in detailed reasoning with multiple retrievals, while reinforcement learning without search relies only on the model's existing knowledge. By using retrieved passages, Search-R1 helps the model refine its reasoning iteratively, leading to more accurate responses. Second, we notice that after the second retrieval round, the model has enough information to answer the question. However, Search-R1 performs an extra retrieval step to verify its conclusion, boosting its confidence in the final answer. This aligns with findings from reinforcement learning without retrieval, showing that reinforcement learning can promote verification-driven reasoning, even when search is involved.